can't play any favorites, so I have to be as rude to my friend Venu Veeravilli as I have to the other speakers. So I'll just say, as Venu said, another wonderful colleague who I abandoned in Illinois.
That's right. He was also. I also was a student in the first class that you ever taught at Illinois.
That's right. So Venu survived my and absolute, fantastic work in information. Hypothesis testing, information theory that we'll hear about.
Great. Okay. Great. Thanks. All right. So this is quite different from the talks we've heard so far today, I think, but it still it falls under the theme of inference and high-dimensional data. What's the theme of this workshop? Cognition. No, of the workshop itself. I thought it was something to do with inference, though, in high-dimensional data. Oh, it was the other one. Okay. All right. Okay, so this is joint work with my student Yun Lee, who was actually a student I inherited from Sean when he left Illinois. Very good student, and then a postdoc of mine, Siran Nithinavarath. So you might have heard of the term outlier detection in many contexts, and this is an old problem. You have a sequence of observations, and the normal observations follow some known generating mechanism or distribution, and there are a few outliers that follow a different mechanism. So in this picture here, those outliers are in red. Okay, and the goal of this problem is typically to get rid of these outliers, to winnow them out. They're like worms and grain, and you want to get them out and get rid of them. And why might you want to do that? You might use it for something like cleaning up the data if you want to do statistical analysis on it. So they may turn out to bias your distributions. And so, for example, if you want to make your detection statistic robust, you might remove outliers before you do your decision making. Okay, and there are some standard ways to do this. A lot of literature on this. For example, you could compute some kind of statistics on these distributions, on these observations, and then have a metric that if I'm so far from the mean, say in terms of Mahalanobis distance or something like that, I can throw out those guys that are outside that distance. Okay. The problem I'm going to talk about is slightly different. You can think of it as a problem where there are a significant number of outliers, or there's like a batch of grain that has only worms in it, or many worms in it, and there are other batches of grains that don't have any worms, and you need to identify the batch that has the worms and throw the entire batch out. Okay, so we have streams of data. Okay, so I have m coordinates, and I'm observing n observations in each of the coordinates. Okay, so I have you have n vectors, one at each point in time, and I need to figure out which ones are the outlier coordinates. Okay, and since the outliers, I typically think of them as being much smaller than the typical coordinates, the number of them. Okay, and I'm going to look at a universal setting, or completely universal setting. That's what I'm interested in, where I may not have any distribution information about either the outlier coordinates or the typical coordinates. Although in practice, you might know something about the typical coordinates. Okay, and I'm assuming there's no training data. Okay, so I'm just doing this online without any prior information. So that's the goal. Right? See this? Now, where does this kind of problem arise? It arises in many different contexts. If you look at fraud detection, say in credit card fraud detection, you might be monitoring many people who have similar buying behavior. Okay, and then you might, if you notice that one of them is behaving differently, you want to catch that quickly. Right? There are other applications as well that I've listed. You can also think of finding outliers for more positive reasons than in fraud detection, for example, where in spectrum sensing, the outlier might be an opportunity to transmit on an available channel that's free when you're sensing a bunch of different channels. And also high frequency trading, although I'm not sure that's necessarily positive, positive applications, but opportunities for making money you can exploit the opportunity to make money if you can identify these outlier streams, right? Okay, that's the idea. So this is the outline of the talk. I'll talk about what happens when you have a single outlier first, just to set things up, and then I'll talk about what happens when you have more than one outlier. Okay. So here's the model. So outlier, I'm going to assume, has a distribution mu. When you have one outlier, that is, and all the typical distribution, all the typical streams have distribution pi. Okay, and the only assumption I'm going to make is that pi is different from mu, and they both have full support. And again, this is all in the discrete world. So these pi and mu come from a finite alphabet. Okay. All right. So this is the picture here. All right, so I have these streams. The first stream has distribution pi, second is distribution pi, the third in this case is the outlier distribution mu. Okay, and we can set up a mathematical model for this. I'm going to assume things are IID in time, and I'll say something about the end, about how you can generalize this to when it's not IID. So the observations in each of these streams are IID with that distribution pi, of course.
It's a systematic thing, then it's a consistent.
It's a consistent thing, exactly.
It's not like you get. I mean, usually you think of an outlier as being
that's why it's different.
Large deviation or something like that.
That's why this is different from outlier detection. That's why I call this outlier hypothesis testing. So this is the hypothesis that the outlier is the third stream is that outlier is that hypothesis.
What makes mu the outlier? Why do you call pi the outlier? Like, what's the difference between pi and mu in this?
Okay, so in this example, I just said there's only one outlier, and m is large, and the number of streams is large. So it has to be bigger than 3 for it to make any sense.
Okay, so you're going to assume that the fraction of coordinates of the outliers goes to 0 or something like that.
Well, we'll get to that a little bit later. For right now, there's exactly one.
Okay.
There's exactly one outlier stream, so that's the easiest problem to consider. All right. So again, the joint distribution of these observations, of course, the outlier has distribution mu, and the other guys have distribution pi, and that's the product.
You allow for the possibility there are no outliers?
Yeah, we'll get to that in a second too. This exactly one outlier is what I'm going to talk about.
Exactly one, okay.
Exactly one. Okay, we'll talk about all those generalizations in just a minute. Okay, so and I'm going to, just for convenience, I'm going to just call this function, this is a likelihood function for hypothesis I, and I'm just going to denote that as Li. It's a function of mu and pi in this manner. Okay, so we'll come across this expression many times in this talk, so I wanted to give it a very compact notation. That's why I've done that. Okay. All right, so nothing is known about mu and pi except that they're distinct, and our universal test has to map my observations, all these observations, the entire vector, over time, and actually that's a matrix of observations. I have to map that matrix to the set 1 to m, and that mapping should not be a function of mu or pi because it's universal. Okay. Now we can, of course, if we can define error probability. The error probability of a decision rule delta is a probability that that delta is not equal to I. I should have had some. There's some. Oh, this is the probability that I made the wrong decision. I think that this notation is bad. I should have. Delta is not the true hypothesis in this case. Okay, so my decision doesn't map to the true hypothesis, and it's going to be a function of mu and pi, of course, and the error exponent, of course, is defined in the natural way. And a test, I say a test is consistent if the error probability goes to 0 as n goes to infinity, and it's exponentially consistent if the error exponent is positive. Okay, the standard definitions. Okay, so before we study our problem, just let's go to some very basic hypothesis testing stuff, right? Background. Okay, if I have two hypotheses, the hypothesis 1 says that the distribution is pi, hypothesis 2 is the distribution is mu, then I know that the best test that minimizes the error probability, or since or rather maximizes the error exponent, is the maximum likelihood test, which just chooses the hypothesis with the larger likelihood function or log likelihood function, and it's exponentially consistent, and the exponent is given by the Chernoff information, which is this expression here. And actually, a special case of the Chernoff information is where you set s equal to half in this maximization, and you get what's called the Bhattacharya distance between the distributions. Okay, and the Bhattacharya distance will turn out to play a more important role for the problems we're going to be talking about in a minute. Okay, but the reason I put this up is, what happens if I don't know distributions here? Can I construct something universal? So for example, if I knew pi, but I didn't know mu, can I construct a universal test? Okay, so let's ask that question. So if I know pi, I don't know mu, actually you can show that for any test that you design, I can find a mu such that the error exponent is 0. So I cannot actually construct a test that's exponentially consistent without knowing both distributions. And the way to think about it is, so if I knew pi, I could put a little decision region around pi, say a divergence ball around pi. If I fix the radius of that divergence ball, then if mu falls inside the divergence ball, I'm not going to be able to drive the error probability to 0 exponentially fast. So I have to shrink the ball, but as I shrink the ball, what's going to happen is that I have to make it shrink all the way to pi as I get more and more observations, and then I'm going to lose exponential consistency. I can make the test consistent, I can drive the error probability to 0, but I cannot make it exponentially consistent without knowing mu, because mu could be arbitrarily close to pi. So that's the problem. So without knowing mu, I can't hope to get exponential consistency. Okay, and that's going to be very different from what we'll see happens when you're looking at the outlier hypothesis testing problem, where we'll see that without knowing either distribution, you can still drive the error probability to 0 exponentially fast. Okay, so all right. So let's look at the one outlier case again. Let's go back to this problem. Right? So suppose I knew both mu and pi. This is a standard multi-hypothesis testing problem. And the optimal solution is the maximum likelihood rule, which will just choose one with the largest likelihood function. Here mu and pi are both known. I'm going to get to the universal case in just a minute. And what's the error exponent in this case? It turns out to be the Chernoff information between this joint distribution mu pi and pi mu, and that turns out to be just the 2 times the Bhattacharya distance. It turns out the optimizer S, due to this symmetry, is a half in the Chernoff information. That's why you get 2 times the Bhattacharya distance between mu and pi. And so if you think about it pictorially here, if we look at hypothesis 1 and hypothesis 2, they only differ in the first 2 components, and they differ symmetrically like this. And so you get 2 times the Bhattacharya distance as the error exponent. Okay. Now suppose mu is unknown. Okay, let's first take the case where pi is known. So the typical distribution is known, but I don't know the atypical distribution. Okay, that might be a case that arises in practice where you have a lot of time to learn typical behavior, but you may not know what the atypical behavior is going to be. So in that case, what we're going to do is simply replace the distribution mu by its maximum likelihood estimate, which is the empirical distribution, and form a generalized likelihood. Okay, that's a natural thing to do. And it turns out that this generalized likelihood test is also is exponentially consistent. Here's a case where, unlike in the binary hypothesis testing, you can actually construct a test that's exponentially consistent, and it actually has the same error exponent as if we knew both mu and pi. Okay, so that's somewhat surprising that you don't lose anything by not knowing mu if you know pi. Actually, the reverse is true. You can also construct a test when you know mu but you don't know pi that's exponentially consistent and has the same exponent. Okay, it's a slightly different test though that does that.
But how can you do this if you don't know which one is the outlier? I mean, let's say I just choose the first coordinate to use it to make the empirical distribution.
So this is the ith hypothesis. This is the likelihood function I use for the ith hypothesis. And the ith hypothesis, I take the ith coordinate and replace the distribution for that coordinate by the empirical distribution.
I see, okay.
And I do that for every coordinate.
Okay, yeah.
I do that for every hypothesis and choose the one that has the largest likelihood. It's a natural thing to do.
Yeah.
Okay. Now it turns out one thing to keep in mind is that I couldn't get to this error exponent by doing something component-wise. So if I tried to test whether each component is pi or mu by testing pi against mu, I couldn't achieve anything that's exponentially consistent, because we know that just binary testing between pi and mu cannot achieve exponential consistency. So you really have to look at everything together. And when you look at everything together, you get information about mu that's sufficient to make it exponentially consistent.
And you don't pay a penalty with the dimension or the number of tests? Or you don't pay
I'll be looking at what happens when m gets large in a minute. Yeah. Of course, the key tool, of course, is Sanoff's theorem. Actually, the proofs are quite simple. The things get more difficult in the sequential setting, but in fixed sample size setting, it's just Sanoff's theorem. But it's just different, more messy applications of Sanoff's theorem. But that's all it is. Okay. All right, so now let's look at what happens when both mu and pi are known. So when we know that when pi is known, but mu is unknown, you can get this. And the first question we ask is, can we achieve this without knowing pi also? And it turns out the answer to that is no. You can actually find a counterexample. And the way to construct that counterexample actually is pretty intuitive. What you do is look at two possible situations. One is where the outlier distribution is p, and the other, the typical distribution is p bar, and the reverse situation where the typical distribution is p and the outlier distribution is p bar. And p bar are some different distributions, right? Then suppose you can show that if you can construct a universal test delta that doesn't use any information about p or p bar, right? And look at its error exponent. If I achieve an error exponent of of this, basically corresponding to p and p bar, for this situation, the universal test has to work whether this situation happens or that this situation happens. So one could show that if I achieve the maximum error exponent for this situation, then I'll have to have an error exponent of 0 for this situation. Reverse the distributions. So I couldn't possibly achieve what I would get with known mu and pi. Okay, so I have to lower my expectations a little bit. Okay, but I can still ask to see if I can get positive error exponent. So that's the next question. So again, we'll construct the universal test the same way we did when only mu was unknown. So what we'll do is compute a maximum likelihood estimate for the for mu for the ith hypothesis as the empirical distribution for the ith stream, and then take all the other streams, average them, and produce an estimate of pi for the ith hypothesis. Okay, so that's what I plug in to my likelihood function, and then I apply the generalized likelihood principle. I just choose the one that has the largest likelihood function. Okay, again, this is a natural test to use. Okay, so you can construct other tests that you can easily show that are consistent, but not necessarily exponentially consistent. Okay, so this test construction turns out to be at least the best we could find, and we can actually show some asymptotic optimality property of it. Okay. All right. So everyone see how we construct this test? Okay. So if we actually compute the error exponent for this test through Sanoff's theorem, we get it as a solution to an optimization problem. Okay. And basically the decision regions which are determined by these likelihood functions dominating other likelihood functions can be written in terms of Kullback-Leibler divergences, which is where these guys are coming from. Okay, so it's a constrained optimization problem. It turns out to be non-convex, so you really can't solve this easily. But you can find upper and lower bounds on the error exponent. Okay. And you can actually show that it's strictly positive. So So you have exponential consistency. You're not going to get the same error exponent that you would get when mu and pi are known, but at least it's exponentially consistent. Okay, first of all, because the upper bound is trivial. It's the same as when mu and pi are known. That's a trivial upper bound. Okay, what about the lower bound? Actually, you can find a lower bound. It's a messy expression. I don't think I put it down on a slide. But the interesting thing about the lower bound one could show is that the lower bound goes to the optimal error exponent when mu and pi are known, when m is large. Okay, here again, going back to what we were talking about this morning in Ken's talk, I have to let n go to infinity first, and then let m go to infinity for this to work. I don't know what happens when I make n and m go to infinity together yet. Okay, so think about, I've computed the error exponent, and then I look at the behavior of the error exponent as m gets large, and I can show that goes to the optimal error exponent. And what's the intuition behind this? Well, when m gets large, I can get a very good estimate of pi by just averaging across all coordinates. Because there's only one outlier coordinate, and that it doesn't play much of a role when m is large. I get a very good estimate of pi, and when pi is known, I know that I can achieve 2 b mu pi. Okay, so it's not surprising that I can get that. All right, now let's get to Max's question. What happens if I allow for the possibility of no outlier? So in addition to those m hypotheses corresponding to the first, second, and so on being outliers, what if there's a hypothesis corresponding to no outlier, where the joint distribution is just determined by the pi? Well, you can actually show that you cannot construct a universally exponentially consistent test. Okay? And this is true even if pi is known. And this reason for that is exactly the same as the reason why you can't construct an exponentially consistent test for the binary hypothesis testing between pi and mu. Right? Because if you think about it, when hypothesis 0 happens, I get no information about mu. Right? And so I couldn't possibly drive I couldn't put a decision region, basically, a decision boundary between the 0 hypothesis and the other guys to drive the error probability to 0 exponentially fast. Okay? And also that's why things work when I know that there is exactly one outlier, because no matter what hypothesis happens, I'm getting some information about the outlier distribution. And I'm exploiting that in the optimal way to drive the error probability to 0 exponentially fast. Okay? But we can do something in this case. And what we can do is, since we can't hope to drive the error probability to 0 exponentially fast, we can at least drive the probability of 0 to 0 at some rate, right? And then and hope that we can get exponential consistency under all the other hypotheses, and we can do that. Actually, it's a very simple test construction, simple generalization of what we had before. Instead of simply using the likelihood function, what we do is make sure that that likelihood function is large enough relative to all the others, right, by some factor lambda. Okay. That's actually going to 0. And it's similar to when I talked about binary hypothesis testing. You're shrinking the decision region around 0, around pi, down to pi. It's a similar thing that's happening here as well. And if it's large enough, you decide in favor of that hypothesis, otherwise choose the 0 hypothesis. Okay? And this test turns out to be consistent under the null. You drive the error probability 0 under the null, and exponentially consistent under every non-null. And in fact, has the same, you can compute the same lower bound, or you can show that the lower bound on the error exponent for all the other hypotheses is the same as in the case when there was no null hypothesis. And you also have asymptotic optimality, in the sense that as m goes to infinity, you get the same error exponent Okay, so the behavior is really good for all the non-nulls. So from a practical viewpoint, if there is an outlier or if there's fraudulent activity, then you can catch that quickly. If there isn't, it might take you a long time to say that nothing bad's happening, but that's okay probably. All right, so what happens when there are multiple outliers? So things get a little more complicated. Okay, so first of all, if there are multiple outliers, there's no reason for the different outliers to have the same distribution. Typical distribution you can assume is the same, right? Because that's supposed to be typical. But there's no reason for the outliers to have the same distribution. All they need to satisfy is that they have to be different from pi. They may be the same as each other, but they don't have to be. Okay, again, if you want a universal test, you want a test that maps the observations to a set of outliers, okay, which is a subset of the set 1 through m. And it shouldn't be a function of any of these things. Okay, and it's similar to what we had before with one outlier, except now we have a likelihood function with all these outliers belonging to this set S, capital S. Okay, so we're going to assume that the number of outliers is some number t, and the size of this outlier set is equal to t. And let's assume for now that the number of outliers is known beforehand. Okay, so we'll talk about what happens if we don't know the number of outliers in a minute. Okay, and so again, suppose you knew all the distributions, the mu's and the all the mu's and the pi, then you can compute the error exponent. In this case, it's a slight generalization of what we saw before. The error exponent is determined by that kind of a worst case Chernoff distance between these hypotheses I and j. Okay. And if they're identically distributed, then it turns out to be back to the same thing that we had before, the 2b mu pi. Yeah?
So you have to check all subsets S of that size?
Yes, yes.
Does that suddenly become impractical?
Not necessarily. I mean, we're talking about, say, 2 or 3, so it may be polynomial in M. Yeah. If M is large, yeah, but it's not exponential at least, it's polynomial. If M is 1,000, then even 1,000 squared can be large. So yeah, but you know, 1 or 2 might be typical. Okay, so again, what's happening here is that if the outliers are identically distributed, if you look at any 2 hypotheses, they'll still differ in exactly 2 components, where one is a pi and the other is a mu. Everywhere else, they'll be matching in the pi or the mu, and so you end up getting to b mu pi again. All right, so what happens if the mu's are unknown and pi is known? Again, that might happen in practice, where you know the typical distribution. Then, again, we can construct the rule in the same manner. Just replace the unknown distributions by the empirical distributions, and construct a generalized likelihood test. And you can show that it has this error exponent, which is actually smaller than what you get in this case when, unless of course all the mu's are the same. If the mu's are different, this error exponent that you get, you lose something by not knowing the mu's. Okay. But it's still exponentially consistent. And what happens if you don't know both? Then again, you do the same thing we did before, slight generalization. You replace all the mu's by their empirical distributions, and then take the remaining components and average them out to get an estimate for pi for that hypothesis. Plug it in, and then you can show that this test is a little messier expression, but it's still a solution to an optimization problem, and it has a positive error exponent. Okay. Unfortunately, these results are not going to be as nice as in the single outlier case, in the sense that what happens is, if you look at so let's see what happens. First of all, there's a loss from just not knowing if you don't know, if you know the pi and just don't know the muse, okay, that serves an upper bound to the case when you don't know anything. And then what happens? Oh yeah, sorry. In this case also, one can show that you have asymptotic optimality in this sense, in the sense that you get the same error exponent as if pi were known and the muse were unknown as m goes to infinity. But you don't get this upper bound, of course, because even when you know pi and you don't know the muse, you don't achieve the optimal error exponent. So, but at least you achieve what you can if just pi were known. But of course, if the outliers are identically distributed, then these two collapse to the same thing, and you achieve the optimal error exponent. Okay, so things don't look too bad if you know the number of outliers beforehand. Okay, but if you don't know the number of outliers, then of course things get much harder. First of all, you can prove necessary and sufficient conditions for the existence of an universally exponential consistent test. You cannot include the null hypothesis. Of course, we already knew before that that doesn't allow you to get an exponentially consistent test. And you have to have them all be identically distributed in order to get an exponentially consistent test. And one of the reasons for this is that the muse can be arbitrarily different from each other. And so you might be able to learn something about one of them, but not any information about the other when you look at a particular hypothesis. So that's what's going on, and you really need information about all the distributions in order to be able to construct a good test, an exponentially consistent test. Okay, but if you had some kind of condition that said that all the outliers will come from some class, of distributions you know beforehand, okay, and that's different from pi, then you could still construct an exponentially consistent test. Okay, but if you don't have any information about the muse whatsoever, then there's no hope. You can't construct an exponentially consistent test.
Is it apparent that there's no monotonicity in the x in some sense of the size of your x? I almost expected you to tell me that life will be okay, because like as you know, you have more outliers, they can become either easier or harder. You know, it's kind of counterintuitive with the fact that. But
you have to. Well, what happens if you have a large number of outliers, or you could have more than one outlier, for example, you can still construct a test that's exponentially consistent as long as they're all the same. That you can show. But if they're different, what happens is, again, they can be different arbitrarily, and then there's no way to construct a good decision boundary between the hypotheses anymore. That's what's going on. Okay, I think that's it. Am I doing okay on time? Yeah. Okay. All right. Let's. I want to say a little bit about some extensions, though. So I think we understand the fixed sample size setting pretty well for both the case when you know the number of outliers and you don't. At least in one case we know we have some negative results, in the other case we have some reasonably good positive results. I think the more interesting stuff in practice might come when you look at, first of all, extensions to non-IID observations, I think would be interesting. I don't know what kind of tools one needs to go beyond the IID case. Sean might have some comments on that. And what kind of error exponents you can expect to achieve then. I guess some Markov, appropriate Markov models, I guess, for the observations might be interesting to study. The sequential setting is quite interesting as well, and this problem turns out to be much harder, and we don't have as good results in this setting. So the sequential setting is when the observations are coming to you one at a time, and you need to make a decision as to when to stop and declare one of them being an outlier hypothesis. We could show that you get a better error exponent in the sense that if you look at the expected stopping time and how it behaves, how it's related to the log of the error probability, that error exponent one can show is at least as good as the Kullback-Leibler divergence between mu and pi, okay, which is bigger than 2 times the Bhattacharya distance. So you do better than in the fixed sample size setting. But one can show that if you knew the distributions, you could actually achieve 2 times. Rather, you can achieve an error exponent that's d mu pi plus d pi mu. So you lose one of the terms when you don't know the distributions. So I'm not sure. So we don't have any asymptotic optimality results, even with one outlier in the sequential setting. It seems to be much harder. And the analysis also is quite different. It requires tools from renewal theory. So, and actually some nonlinear renewal theory if you want to go beyond the basic results. So that's it's a much harder problem. The quickest detection problem is also interesting, I think, where you might have a situation where nothing is happening, so all the coordinates are typical, and then one of them changes to atypical. And you want to detect that change quickly. And I still don't know how you can construct a good test in that setting. Okay, so that's where I'm going to stop. Yeah.
So you proposed a ML test for detection. You were allowing for the null hypothesis, right?
Yeah, yeah.
So you basically compute the maximum likelihood, and basically you're looking for a right that is big enough. Like,
yeah, exactly. So I think you want that difference between the maximum and the second largest, essentially, to be large.
So imagine that you can you apply the same test? Imagine that you don't know the number of outliers, but you know that they are small while m is going to infinity.
Right.
Let's say they're constant or even like log
Right.
m or something like that. Can you just compute this and look for spikes? Because basically when you compute this and if m is large enough, even though there are other outliers, because there are really very few of them, the effect of them will going to be dying down because you're going to have 1 over n minus 1 for everybody else. So basically, compute this and look for spikes that are big enough compared to the rest of them, and those would be your candidate for outlier. Is there something formula to this?
So that, but that's, again, that would work if, you know, you're saying you want to catch the outliers one at a time, in some sense, right? Sequentially.
Yeah, not sequentially. You have all of them. You have all the data. I'm not talking about the sequentially. You have all m coordinates and you have all of the observation that you have, just like this setup.
Yeah.
But you have more than one outlier.
Right.
You don't know how many.
You don't know how many.
But you know that there are very few compared to m.
Yeah.
So can you just do something really naive like this? And
No, you can actually show that you cannot construct an exponentially consistent test unless you know. Yeah. You can construct good. Yeah, you can construct consistent tests. You can always do. Yeah. If you're happy with that, then there's many ways you can do that. But we were looking for exponentially consistent tests. Yeah. All right. Thanks.